Chemical bonding. We have two major categories of compounds that you used to learn in grade 9 and 10. And those are ionic compounds and molecular compounds. Molecular compounds are also called covalent compounds. Now, ionic compounds, we were learning in grade 9 and 10 that they form from metals combined with nonmetals. And then we have ionic compounds that essentially what creates them is the ionic bond, the electrostatic attraction between positive and negative ions. Molecular compounds are formed between two nonmetals. Essentially, they share electrons between the two of them, and those are called covalent bonds. It's the valence electrons that decide what type of compound you're going to be dealing with. The valence electrons, remember, are the ones that are in the outermost orbital. There's two situations. One is that there's a transfer of electrons from a cation, well, from a metal atom to a non-metal atom, and that is what creates an ionic bond. The other situation is where electrons from both atoms pair up and form a bond between the two atoms, which is called a covalent bond. So when the metal transfers its electrons to the nonmetal, that's when we have the creation of the ions. So the metal, which loses electrons, becomes a positively charged ion, or a cation, and the metal that accepts the electrons or receives the electrons is called an anion, a negatively charged ion. The electrostatic attraction then of the opposite charges of those ions then creates the ionic bond. So for example, sodium and chlorine. Sodium has one valence electron, chlorine has 7. Sodium wants to lose one electron, and chlorine needs to gain one electron. So the sodium electron leaves the sodium atom and joins the chloride ion. You can just barely make out my black arrow here. I should probably change that to another one. But anyway, once that happens, we now have a situation where we've created a positive sodium ion, or a cation, and a negative chloride ion, or an anion. Now, for some situations, it may be necessary to transfer more than an electron, and it may be necessary to add additional types of atoms in order for the change to be electrically neutral, because that's the bottom line, is you have to have the cations and anions in a ratio that makes them electrically neutral. So the overall charge has to be 0. So let's take a look at oxygen and aluminum. Aluminum has 3 electrons in its valence shell that it wants to lose. Oxygen only needs 2. So we have a situation here where the aluminum, well, if it gets rid of 2 electrons, they go to the oxygen, 1 into this spot, 1 into this spot, and then that leaves us with the extra electron on the aluminum, so it has to go somewhere. So it goes to another oxygen, which grabs 1 electron from another aluminum. That other aluminum now has 2 extra electrons, which need to go somewhere. They go to another oxygen. And so now you can see that once this is all done, now we have a situation where we have 2 aluminums and 3 oxygens, and the overall charge turns out to be 0. Ionic compounds and covalent compounds are very different from each other. Some of the properties of ionic compounds, they have very high melting and boiling points. And that's because the electrostatic attraction between the ions is a very strong attraction. Molecular compounds, on the other hand, have very low melting and boiling points. Again, because the attraction between those compounds is somewhat weaker, actually quite a bit weaker than the attraction between ions. And there's a whole range, because you can have fairly strong attractions and you can have very weak attractions as well. Ionic compounds, when they dissolve in water, for example, they form what we call an electrolyte, because the water molecules can get between the ions, if they're not held too tightly together, and pull them into solution. And if you have ions floating around in solution, then you have a situation where you have the possibility of electrons to flow through that solution. It conducts electricity. The molecular compounds, though, because they don't have charged particles in solution, if they do dissolve, for polar substances, for example, then you have a situation where electrons can't flow through that, and it's a non-electrolyte. With ionic compounds, you don't have individual molecules, you have charged particles, cations and anions. The solids are soft, usually because they break apart fairly easily, because the intermolecular forces aren't too strong, and you have individual molecules forming as well. When nonmetals combine with nonmetals, they share the electrons between them to create the bonds. So the electrons pair up. Those bonds are always pairs of electrons. They do that so that the atom will see, at least part of the time, a full valence shell. In other words, 8 electrons in the valence shell, 2 for hydrogen. So, for example, HCl, or water, or ammonia, or methane. These Lewis dot diagrams show how the electrons pair up in order to create the bonds between each of these central atoms and the hydrogens. There are some situations where you get multiple pairs of electrons, and that again is to satisfy that octet rule where you have a full valence shell. So oxygen, molecular oxygen, for example, the 2 pairs of electrons join together to create the double bond, 3 pairs in nitrogen to create a triple bond. Carbon dioxide is an example where you get 2 sets of double bonds. The shape of a molecule also has a bearing on its properties. So, for example, when you have let's say a polar bond, there's charge distribution when one of the atoms is more electronegative than the other one. But if the overall shape is symmetrical in 3 dimensions, then you may have a situation where you in fact have a molecule that is non-polar. These are some examples. The carbon-oxygen is a slightly polar bond, but because they point in opposite directions in CO2, CO2 is non-polar. Methane, this shape is actually not flat, it's a tetrahedral shape, but all the polarity that's pointing in one direction is countered in the other direction by the other 3 bonds. The ones that are essentially made of the same atom, well, because the bonds themselves aren't polar, the molecules aren't polar either. Asymmetrical molecules, if the shape is not symmetrical in 3 dimensions, then they will most likely be polar, at least to some extent. Okay? How polar depends on how polar the bonds are and how much that charge separation occurs. Whenever bonds are broken, energy is absorbed, and whenever you form a new bond, energy is released. The reason for this is the atom tries to get into a stable configuration as much as possible, and so to do that, it will, when it forms a new bond, it becomes more stable and therefore goes to a lower energy state, releasing energy in the process. So the whole point of bonding with other atoms allows a particular atom to attain a stable valence electron configuration. Noble gases, for example, already have that, and so they don't tend to bond with other atoms. That's why we call them noble gases. Alright, so here's a list of the relative strengths of these intermolecular interactions, the intermolecular forces. Ionic solids have very strong, not so much intermolecular forces, but interionic forces. These are the strongest attractions. Molecules with hydrogen bonds are also fairly strong. And then we have polar molecules, and then we have nonpolar molecules, which are with the weakest. Now we can diagram this stuff with using Lewis structures or Lewis dot diagrams, and that shows us the arrangements for the valence electrons, because that's all we're interested in, around a particular atom. So fluorine, for example, has 7 valence electrons, and we show that like this. If we make fluorine an ion, where we give it an extra electron, then we indicate all of the 8 electrons, put square brackets around it, and the charge of the ion outside. For molecular compounds, we can show that like this, where they're bonded together, sharing the pair of electrons that are between the two. If we have a cation that gives away electrons, then we just simply show no valence electrons and put the charge outside, like in the sodium. An ionic compound where we have to show both ions, like let's say sodium fluoride, then we show it like this, where we show the anion with the square brackets and the negative charge, and the cation without any electrons and the positive charge. So the dots represent the valence electrons, the outside shell of electrons. We call this the kernel. The inner electrons are the kernel, and it's not, we don't need to represent that part, so we just ignore the kernel, and we just show the valence electrons. And I already mentioned when an atom loses electrons and becomes a positive ion, we show that in this fashion. And when an atom gains an electron, becoming an anion, we show that in this fashion. Ionic compounds are shown in this form, although you could write it with just this right half and then put a subscript outside the fluorine. That's an acceptable method as well. Now, rules for drawing Lewis dot diagrams. In class, I normally, on the board, do a simultaneous Lewis dot diagram for carbon dioxide with this, but that's not possible with the voiceover, so we'll just go through the rules. The first thing you do is count all the valence electrons for each of the atoms in the molecule. Then you add or subtract if you're dealing with an ionic charge. For example, in the polyatomic ions, it's possible to do the Lewis structure for those. Then you write the symbol for the central atom, place the other atoms symmetrically around it, place the bonds from each atom to the central atom, 1 pair of electrons each, and normally you do that with a dash rather than the 2 dots. Then you complete the octets for all atoms except the central atom, Except hydrogen, of course, it doesn't really have another because it's already taken care of the one electron in the bond. And then you move pairs of electrons in to create double or triple bonds if it's possible to complete an octet for the central atom. And if not, you don't worry about it. So let's do the carbonate ion as an example. So we have carbon with 4 electrons, we have oxygen with 6 electrons, 3 of them in the compound, so that's 18 electrons. There's a 2- charge to the whole thing, so that's 2 extra electrons, total 24 electrons. So then we write our carbon as a central atom. Usually it's the most electronegative one, or sorry, the least electronegative one that becomes the central atom. Not always, but most of the time. All right. If it's carbon, then it's usually the central atom. Oxygens then go symmetrically around it. Put a dash in between for each of the bonds. That takes care of 2, 4, 6 electrons. And then 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 electrons. And now, because we're dealing with a polyatomic ion here, we got to put the charge, right? So square brackets around it, charge outside. And now we've come to a situation where everything has a stable octet. You'd think we were done, but notice the central atom, we have a situation where we don't have a stable octet around the carbon. All right, so now that we got to decide, is this actually the proper structure? Because if we were to move a pair of electrons in here and create a double bond, we would have another structure, but then that would kind of fulfill what we want to do. To decide, we look at a thing called the formal charge. And the formal charge is simply the number of valence electrons minus the number of bonded electrons minus the number of number of unbonded electrons minus the number of bonded electrons divided by 2. All right, so how does that look? Okay, for CO3 2-, let's go through, set that up again. To calculate the formal charge for oxygen, 6 minus 6 minus 2/2 gives us -1, but all 3 of them are the same, right? So we have each one has a formal charge of -3. The carbon is a 4 minus 0 minus 6/2 is equal to +1. Add those two up and you get a -2 formal charge, which makes sense because the overall charge of this thing is -2. All right. Let's take a look at this other option where we take a pair of electrons and we put it into the middle to create that double bond. All right. Now let's look at the formal charge for this. Oxygens. We've got 2 types of oxygens here. The singly bonded oxygens look like this, same as before. The double bonded oxygen, though, looks like this. 6 minus 4 minus 4/2 is 0. All right. And then the carbon is a 0 as well, because now it has 8 electrons instead of just 6. All right, so now as a result, we have a situation where we have 2 things that have formal charge of 0, whereas before, we only had the 1. We actually didn't have any with a 0 overall charge. Having more atoms with a 0 formal charge is preferred. So we have a situation then where this structure is preferred over the other one. All right, so if this structure is preferred, how do I know that double bond goes there and not, let's say, in this position? Okay, or perhaps in this position? Well, it turns out that for this particular structure, all 3 are valid. It's just a matter of kind of turning it. And you would think, well, though, you've got single bonds and you've got double bonds, so this is an asymmetrical molecule. And if that's the case, then wouldn't that show up in all of our images of this particular substance? And it turns out that when you look at this under an X-ray crystallography, it turns out that all of them are the same. Well, if all of them are same, then this particular theory, which is supposed to explain what's happening here, doesn't work. So we have to modify our theory a little bit. And so what we say is that, well, what happens here is the double bond flicks from this position to this position to this position, back to this position, and keeps going around so fast that essentially the overall effect is that all three bonds are exactly the same length. And so as a result, we call this a resonance structure. Okay? It's not really one or the other, it's a combination of all three. All right? And so that's kind of how we modify this theory to explain this phenomenon. All right. So anyway, we're going to give you some work on Lewis structures and such, and this is the homework exercise. Spend some time doing that. Ask me if you have questions.